So hello and welcome to this Arrow lecture on materials of challenging environments, looking at nuclear materials with this mini lecture a focus on current fission. So I'm Dr. Sandy Knowles. I'm Associate Professor at Nuclear Materials at the University of Birmingham in the UK. And I'm also a UKRI Future Leaders Fellow working kind of on advanced nuclear materials. So I work both in research and in teaching. So a great thanks to the Arrow Initiative for inviting me to give this mini lecture and to the GCRF and UKRI for supporting this initiative. Looking in the kind of nuclear sector, there's quite a wide range of applications that we can really consider. In many countries, this would be considering primarily, we'll think of nuclear power generation, so using uranium. There's concepts then such as generation 4 fission, which is sort of new generations of reactors. There's a huge amount of work in medical, so using labeling elements, and so fluorine or technetium, where we can also do imaging using these advanced techniques. So there's a lot of that done in the University of Birmingham. So we link to the Queen Mary Hospital, where we can produce isotopes in the university and then use them with patients in the hospital setting. There's also work looking at doing treatments, so things like gamma ray irradiation or proton beam therapy. We can also use nuclear or understanding of nuclear to do metrology and things like radiocarbon dating, particularly looking at carbon-14, so one of the isotopes of carbon. We can use that to date things to very good precision and help us to understand things in the past of the world. We then have things in domestic applications. For example, americium is used in smoke detectors, so many people might be able to have access to these in lots of environments. Unfortunately, we have the history of nuclear. We have the weapons programs that we used. So this can be both kind of nuclear bombs, but there's also some knock-on effects of nuclear things such as depleted uranium, which might be used just in ordnance, although it's seen decrease use nowadays. We then have maybe some concepts that are happening in space. So there's things like nuclear batteries. So some of the deep space probes, so the things that we kind of use to explore the depths of the solar system. If you go far away from the sun, you can't use solar panels, and so you can use these nuclear batteries. And actually, there's a renewed interest in space applications. So things like how are we going to power a moon base, if that's something we decide to do, and also is potentially a Mars base, and also could use nuclear in order to use the transport, so the propulsion systems to get to Mars. And then where I spend a lot of my time, which is working in nuclear fusion. So this is kind of seen a series of new reactors being built and a tremendous number of startups and private ventures, as well as large government ventures in fusion. So there's a lot of different applications we have, and the nuclear industry is I think on a kind of bit of a revived period with the kind of challenges in trying to meet net zero, as well as kind of having security of supply. So it's a fantastic way for a country to achieve energy independence, and so particularly say France and Japan, this has been key in their sort of strategies for energy, at least in the past. So in these kind of mini lectures, I'm going to really focus on fission power generation, then looking at generation 4 fission. We'll have a lecture looking at space, and then on to fusion. So to start off with, we'll be talking about current generation fission in this mini lecture. So currently there are about 45 nations that generate power from nuclear reactors. In the UK, we get about 20% of our energy or electricity, at least, from nuclear, whereas countries like France, they get over 70% of their electricity from nuclear. And that's an important feature because that means actually 70% of their electricity grid is zero carbon or low carbon. There are about 450 reactors in operation, at least from when we did this kind of data grab. Then there were about 50 under construction and about 150 planned. However, it's been the case that the number of reactors has been relatively constant since around 1980, particularly with what's happened in Europe and the US, where it's been a pause on building, whereas countries like China, Russia, and India that have been continuously building. We have about 69 nations that have research reactors. So for example, in Australia, they don't use nuclear to generate power, but they do have the Opal test reactor, which is principally used in order to generate medical isotopes. And it's important to note that all of these reactors are overseen by the International Atomic Energy Agency, which sets the standards for safety and incident reporting and tries to support when there are issues. So I think an important question when we're thinking about nuclear is why do we need nuclear? Are there not alternative energy sources that we can use? So some of the things which we're talking about now are from this article from MIT, The Future of Nuclear Energy in a Carbon-Constrained World. So with COP 2027, this has been kind of a very important push towards how do we reduce our emissions of greenhouse gases, so particularly carbon. And if we're in the kind of business of trying to reduce carbon usage, then we want to look for alternative technologies to coal and gas that don't use fossil fuels and don't create the associated emissions. And so this is looking at two different scenarios, the one on the left where we don't have nuclear, and on the right where we do have nuclear. So in the bars, the colored bars are showing different types of energy and different generation methods. This is a prediction for Texas. And going from left to right within these bars, so on the left-hand side, we've got the 5 bars, and we're going with an increasing amount of renewables on grid, so particularly wind and solar. And one of the challenges is as we put more wind and solar onto the grid, we're going to need a lot more storage. And so this could be in the form of pumped hydro or in batteries. And one of the challenges is that as you put more and more renewables onto the grid, you have to put more and more storage for those kind of extreme scenarios where you have no wind or no sun for maybe days or even weeks. Or in the UK, we have the challenge of in the winter where we have months of potentially low solar. The benefit here then is if you put a certain amount of nuclear onto the grid, so if we're talking about 20-30% nuclear onto the grid, alongside building out renewables, we can see that on the right-hand system where we have nuclear, the cost of the total installed capacity has been dramatically reduced. And so this is down by a factor nearly of a third. And so this is a really thing. Although nuclear itself might sometimes be costly, it avoids you needing to produce quite as much storage capacity. So the kind of combined cost of renewables plus storage, nuclear helps alleviate the amount of storage that you need. So I think this makes a compelling case as both nuclear as its own technology to reduce carbon emissions, but also as a technology that supports the amount of renewables we can have on a grid. And so I think Texas is a good example compared to the power system you have in South Africa, for example. Lots of similar kind of changes, kind of going from a fossil to increased solar. So solar should be a very promising technology, but potentially that nuclear can play an important role of really getting as much fossil fuel generation off grid. So some of the concerns that then are listed around nuclear, one particular one is around construction costs, and they just say it's too expensive. I think this can be something which varies hugely across the world, and depending on where you're manufacturing. So in historic plants, we had kind of relatively low cost per megawatt hour, whereas in some of our more modern reactors in the UK and the US and Europe, the cost to install and produce a nuclear power plant has dramatically increased. And there's a few different factors as to why that might be the case. So it could be to do with regulations. So over the years, we've put more and more regulation on nuclear. Actually, now it's becoming a lot more expensive to manufacture things in some of Europe and America. But another key issue has been the financing. So this is Hinkley Point C, which is a reactor that's well through build in the UK and should be coming online relatively in the next few years as a kind of new power plant. And one of the challenges, it's not really even just the construction or some of this kind of high technology items, it's really the interest payments. If you have something that takes maybe 10, 15 years to build, and all that time whilst you're building, you're having to pay off interest. And so there is some things that we can do with the financing model in the UK, which we've now done, so these contracts for difference and things like that, where we can share out that interest a bit more evenly, and this can help reduce the cost of the overall thing. This also makes a massive difference if the government itself is also investing into the power plant. That gives confidence to the market and it can help reduce the interest payments. So one of the other concerns, rather than cost, might be safety. So obviously safety is critical for a nuclear power plant. We do have hazardous substances involved. But we have lots of technologies where we have hazardous substances involved. That doesn't necessarily mean we don't do it. Gas in our car can set on fire or potentially explode, but we still use cars. In nuclear, there are specific challenges, and this increases the cost of the facility as well as the capital cost. And particularly, it's very important, these safety procedures, as they're needed to maintain public confidence in nuclear power and really give us this public mandate that this is one of the solutions to some of the crises we face. And we really need to ensure that we maintain a low risk in nuclear facilities, but this is true in any application we want to reduce the risk. And I think in nuclear there is an important consideration of risk versus perception of risk. So when we kind of consider the hazards in nuclear, then we often are considering them in isolation and thinking of some of these extreme accidents that have happened, and they kind of stay in the public consciousness. However, when we consider it to other energy sources, so particularly things like oil and coal, so we have both deaths in terms of the extraction, but a huge number of respiratory deaths in terms of the health implications of burning fuels and the kind of pollution that's caused, particularly with coal. And so in this sense, whilst nuclear there can be accidents, the amount of accidents and actual numbers of deaths we've had compared to the amount of energy we've generated, actually you can regard nuclear as an exceptionally safe technology. That's not to say we don't need to be careful with it, but at least kind of on the history, has really not been as bad as maybe the perceptions have people believe. I managed to find also some data also for wind to add on to this plot. So all the kind of renewables are very, very low and beneficial, and this can be this health argument for avoiding fossil fuel use, as well as the climate emissions and onward deaths that are going to be saved for reduced global warming. There is a real impetus to kind of go away from these technologies. So the final caution might be the issue of waste. So current nuclear fission does generate nuclear waste. These can have hundreds of thousands of year lifetimes. But one of the things is that kind of quite how big a problem is this? So kind of to give a perception of magnitude, in the UK, which we have quite high energy usages, one person's entire lifetime of energy use would fit inside a Coke can. And so that, in comparison to the tons of carbon and coal and things we would be using if we use alternative energy sources. So if we were, say, for example, in the UK, to go fully nuclear, in 100 years, we would create about 4.5 million cubic meters of nuclear waste. So that's about the size of Wembley Stadium for an entire country for 100 years, which, we could even use that waste. Actually, in some technologies, we can use it as fuel for future reactors. So the UK, we have this what's called a geological disposal facility, where we're digging effectively a mine in order to safely store this nuclear waste. And the thing is, compared to some of the extraction that we do, 4.5 million cubic meters seems like a lot, but in the UK, when we were really using coal at its peak, we were extracting 312 million cubic meters per year of coal and burning it and putting it into the atmosphere. So it's kind of a reverse of the problem. We're very happy to extract huge amounts of material from the earth and put it into the atmosphere. In this one, we have to kind of consider the balance of risk between one or the other. Extracting coal and burning it, putting it in the atmosphere, which we know the risk that is causing global warming, versus this risk of if we very carefully take a relatively small amount of area and store this nuclear waste. And for me, the balance of risk is clear that we can control the risk of nuclear waste, whereas with global warming, the climate emergency, we do not control that risk, and we need to change our actions. So that's kind of some of the motivation as to why nuclear. Now some of the bit of the kind of more kind of engineering and materials engineering challenges. So in nuclear, the materials in nuclear power are subject to a relatively extreme environment. We want to use these nuclear reactions in order to generate energy. So that means we have a few things going on. We have neutrons, so these are released by the nuclear reactions. We have high temperatures. We have potentially high pressures if we're using pressurized water reactors. There's stresses involved, and potentially we're in a corrosive environment. So we have to decide what materials we want to use and where. A bit of a kind of introduction as to kind of what is a nuclear power plant. So we have within this we have a core where we have a nuclear reaction going on. So for example, the splitting of uranium, which then releases energy. So there's kind of E equals mc squared if we have these kind of arguments, and that's what we kind of use to generate this heat. But in the end, then it becomes just a very sophisticated kettle. And what we're doing is we're generating heat with the nuclear reaction. That's then going to heat water that's going to pass into our reactor over the core, or at least over the fuel cladding. It's going to heat up, and then we take that heat and we take it to a steam generator. So usually we'll have a primary circuit and a secondary circuit. So one that's inside the nuclear environment, one that's broadly outside of the nuclear environment. And then on the right-hand side, everything that's outside of this orange box is pretty much the same as a coal power plant, that we have a steam turbine, condensers. We then use that steam turbine to power a generator. And that's what's creating our electricity. So it's all about this kind of control. There's a lot of other things on the right-hand side, which has been kind of very carefully designed over many years for multiple end applications using steam turbine technology. And then we have the intricacies on the left-hand side, the core, which is what we'll spend our time today talking about. So what we're going to talk about is we're going to go through some of the materials that are, and the demands, the components that are kind of used within a reactor pressure vessel assembly. So we're going to consider the components and then the material and some of the required properties. So we're starting off thinking about the fuel rods. So these are required. What do we want them to do? Well, we want fuel that's going to generate heat. We want it to be stable. We want to kind of know exactly what's going to happen with it. So the predictability is very important. We use a material, we use uranium-235. We actually use it as an oxide. So we use uranium-235 because of the fission reaction that can happen. So we choose a specific isotope. And we use the oxide because it's going to be a high melting point, and also it means it can't oxidize or burn like it could if it were uranium metal. However, we want to make sure we contain this uranium oxide. So being an oxide, it might potentially be brittle. So what we used is a zirconium fuel cladding. So zirconium, the element, we tend to use it as an alloy. The main benefits of zirconium is it has low neutron cross section. So we don't lose many of the neutrons from the fission reaction, and this helps us kind of maintain this stable chain reaction. So that's an important aspect, particularly from a point of view of the amount of enrichment of the fuel, so what level of isotope we need in the fuel. Another aspect for the zirconium, it's sufficiently strong and it has sufficient toughness to make sure it can contain and durably contain the uranium fuel. We then move on to the fuel rods. So in orange on this diagram on the right, so this cross-section of a reactor. So these control rods are in order to reduce the chain reaction. So they need to be able to absorb neutrons, and these allow us to stop any fission reaction. So if we want to either reduce the power output or to completely shut off the reactor. So these use things like boron or indium or cadmium within steel tubes. So that just allows it to be more easily moved around if it's within a steel container. It also gives it that sort of toughness. And these, it's kind of the opposite of the zirconium. We want things that have a high neutron capture cross section. So that's where some of our design of the elements, so we can do that from kind of nuclear physics considerations, and then as materials engineers we have to produce it into a sufficient geometry. And some of the advantage of these putting it in steel is it just allows us to insert and retract the control rods in order to control the reactor. We then have a moderator. So in this, as you have the kind of fission reaction, you can have very high energy, fast neutrons. And actually, in order to promote an onward nuclear reaction in an adjacent uranium atom, actually it's much more effective if we have slower neutrons. So with slightly less energy, they're more likely to create an onward fission reaction. So in order to that, they need to kind of interact with some media. So we use things like graphite or potentially water or heavier water. And so this varies depending on sort of the country usually and the design experience. All of them are possible. And then we have considerations about the stability of that media, but also of the reactor and its operating conditions. So there's certain advantages to certain moderators. We then can consider what the internal structures, so how do we kind of hold all this in place. So these mostly are a structural support for the fuel and the control rods, as well as the kind of surrounding interfaces. So we might use something like stainless steel, so we want something that is strong and corrosion resistant, particularly say if we're in an aqueous environment. And then lastly we have the containment vessels, so the kind of surrounding material highlighted in red. So this is the primary structure. So this is to contain the pressure. So it's a pressurized water reactor. So we have the RPV, the reactor pressure vessel. We kind of really want it to be, we typically use steel based on the kind of the quantities of these things. They can be very large castings, maybe 50 or 100 tons. So there's quite a lot of skill and experience to be able to manufacture the scale of a kind of largely single component, or else to kind of do the welding and to qualify the welds of a welded pressure vessel. We're interested in the steel for the strength. We're particularly interested in its integrity and its toughness, and to ensure that it has going to have sufficient design life, so it's not going to degrade in performance over time, particularly say if it were irradiated, or if there's any kind of corrosion. And also the formability of it is important. We need to be able to manufacture it in quite a large shape, and really to ensure the durability and any flaws to avoid any flaws that might be present in this kind of critical safety component. So that's been a bit of an introduction as to kind of some of the materials that are used in current generation nuclear. I also wanted to kind of label some of the kind of innovations for what's called Generation 3 or Generation 3 Plus reactors. So these are some of the reactors that are being manufactured at the moment. Some of the innovation are ultimately just in the financing. There's a lot of talk of advanced technology fuels or accident tolerant fuels. So these are ones that might be able to reduce some of the complications we had at Fukushima for hydrogen generation during an accident scenario. And also just to have longer fuel lifetimes, so having to do fewer refueling operations. One of the kind of challenges that we've kind of now had as we've used more renewables is that nuclear reactors were generally designed to be turned on and left on, and maybe just refueled or turned down if there's maintenance needed. But increasingly, nuclear reactors are being asked to load follow. So if you have excess renewables on your grid, you kind of like to reduce the amount that you're generating from your nuclear power plant. So you'd rather turn down your nuclear power plant. And that kind of puts different demands on the materials. You're having to do a bit more kind of thermal cycling, which can cause damage to materials and components. So we want to kind of have the predictive capability and durability to do this load following. We have alternative things. We might want to use the electricity to produce hydrogen. So we can use this to kind of generate low carbon hydrogen. And EDF is starting to do this in the UK already. So using the electricity directly. So at times when you have too much electricity, rather than turning off the reactor, you can just use that excess electricity to produce hydrogen. And there's now a lot of interest in this idea of cogeneration. So maybe we can use the heat from a nuclear reactor rather than just using it to generate electricity, which it has maybe a 30 to 50% loss factor, just kind of thermodynamic loss of converting from heat to electricity. If we use the heat directly, then we don't have that losses. So you can do things like chemical process, so things like hydrogen. You could take off that heat directly before going through the steam turbine. You can use it for district heating, and there's many places internationally that do use nuclear for district heating, so for heating homes. And particularly this idea of generating hydrogen. And so this ability to take the heat off before going through the steam turbine and using the nuclear heat directly is being designed into the EDF Sizewell C, which has just had approval to be progressed from UK government. So this is one where we have the option to do this and can use our nuclear reactors in different ways. So it gives us increased flexibility and should ultimately give us a better future. We're going to have these reactors potentially for 50 years of operation, and our demands and our requirements in 50 years might change. And so using nuclear for chemical processes and kind of manufacturing as we go to a kind of a low and zero carbon or carbon negative economy might be very advantageous. So thank you for listening for this mini lecture, and so then there'll be other lectures talking around fusion and generation 4 fission. So I hope you will listen to those.